Welcome to the second part of Unit 4, and this is all about trigonometry. Why? Why do we care about trigonometry? Well, remember what we're working towards. We're working towards two-dimensional projectile motion. And I'm going to give you an example. Let's say we have a standard XY coordinate system. And we have a ball that is launched at some initial velocity that is not along x nor along y. Well, I can write that vector v0 as the sum of two pieces. A piece parallel to the x-axis, I'm going to call that v0x, and a piece parallel to the y-axis. And so now it is the case that v0, we'll do it this, v0x plus v0y equals v0. And what I have up here, if you look, is a 90-degree angle because my x and y axes by definition are at a 90-degree angle. And the x piece is parallel to x and the y piece is parallel to y. So that's also got to be a 90-degree angle. And as soon as I do that, that puts me into the land where Pythagorean theorem and the trig functions are very useful. So let's review the Pythagorean theorem. What I have is a triangle with a right angle. Typically, we let one side be A, one side be B, and the side that's opposite the 90-degree angle is typically called C. And in that case, c squared equals a squared plus b squared. Okay. Or in other words, using my previous example, v0 squared is going to equal v0 x squared plus v0 y squared. If I know two of them, if I know v0 and v0x, or v0x and v0y, then I can find the length of the other side, which is really useful. But what if I don't know the edges of the triangle? What if instead I know one edge and an angle? And in that case, what I have to do is use the trig functions. So for the trig functions, again, we have a right triangle, but we give the sides different names. They're not A, B, and C anymore. What I do is I define an angle. This is the Greek letter theta. The side opposite theta I represent with an O for opposite. The side adjacent I represent with an A for adjacent. And the side opposite the 90-degree angle is the hypotenuse. In that case, the sine of theta is the ratio of the opposite side divided by the hypotenuse. The cosine of theta is the ratio of the adjacent side divided by the hypotenuse. And tangent of theta is the opposite side over adjacent. If you look at this, SOHCAHTOA. That is a way of remembering which trig function is which ratio. So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. The other thing to remember is that if you want to find the angle, you might need to take an inverse function. So theta is the inverse sine of opposite over hypotenuse. And if you haven't watched my YouTube video on calculator usage, I go over how to do angle calculations on your calculator in that. Similarly, I could find theta by the inverse cosine of the adjacent divided by hypotenuse, or the inverse tangent of the opposite over the adjacent. Oftentimes, what we're given is the hypotenuse and the angle. So this would be a question like you have a ball launched at 15 meters per second at an angle of, let's say, 30 degrees. And you need to separate that into the opposite side and the adjacent side. So instead of writing this in this way, what you would have is something like the opposite side equals the hypotenuse times the sine of the angle. Or similarly with the cosine and the tangent. Okay. A couple things to remember. If you're ever in doubt about your calculator, what units it's in, so sine 30 is 1/2. So if you punch into your calculator sine of 30 and you don't get 1/2, chances are that you are in radians instead of degrees. Okay. Other things to remember. If you think about a unit circle, in the first quadrant, sine and cosine are both positive. In the second quadrant, cosine is negative and sine is positive. In the third quadrant, both are negative. And in the fourth quadrant, sine is negative and cosine is positive. So that is helpful. Other pieces of information, sine of 30 is 1/2. This equals the cosine of 60 degrees. Sine of 45 degrees equals the cosine of 45 degrees. And that is the square root of 2 over 2. And sine of 60 degrees equals the cosine of 30 degrees. And that is the square root of 3 over 2. Chances are you'll have a calculator and not need to know these. But if you're preparing to take any of the professional exams, the MCAT, the LSAT, there's an ophthalmological one, there's a dental one. Knowing these basic values of sine, cosine, and tangent and being able to track around the unit circle and get the sign correct of them will be very beneficial to you. Okay, so let's do a couple of examples, more than I've already, I've worked a little bit in there. Let's continue with the previous example that I started outlining. Let's say that the initial velocity is 15 meters per second and it's at an angle of, what did I say on the previous slide? Well, it doesn't matter, I'll make a new angle up, 30 degrees. And you want to write V naught as the sum of two pieces, V naught x plus V naught y. Okay. So graphically, that looks like this. V naught x is parallel to the x-axis, assuming a standard xy coordinate system. And, I guess I should label him. There we go. V naught x. And V naught y is going to be parallel to the y-axis. And I put that arrow in the wrong spot, but we'll deal, right? And just for reference, I'm going to define the coordinate system here, positive x to the right, positive y vertically. So now I can use my trig functions and write that the sine of 30 degrees is my opposite side, that's V naught y, over the hypotenuse, which is V naught, which is V naught y divided by 15 meters per second. That tells me that V naught y is 15 meters per second times the sine of 30. Put that into my calculator. Sine of 30 is 1/2. So V naught y is 7.5 meters per second. V naught x is found with the cosine. So I'm going to write down below and then I'm going to come back up to that. So cosine of 30 degrees is V naught x divided by V naught. So that's V naught x divided by 15 meters per second. In other words, V naught x is going to be 15 meters per second times the cosine of 30. And if I put that into my calculator, that's 13, technically 12.99, but we're going to call it 13 meters per second. Now, watch out. We have this statement up here that says V naught is the sum of V naught x plus V naught y. But notice it's a vector statement. If I take V naught x plus V naught y, 13 plus 7.5, I end up with 20.5. 20.5 does not equal 15. And the reason that doesn't work is by just adding the two components together, 13 plus 7.5, is ignoring the directionality associated with them. It's ignoring the fact that this forms a triangle. If this were a straight line, it would work just fine, but it's not a straight line. Okay. Another thing that students also do is they try to go with absolutes. And that results in them saying, oh, my y component is always found with a sine. My x component is always found with a cosine. This is also not true. So let's do an example where I illustrate how that cannot be true. So let's say that, again, standard x, y coordinate system. I have an acceleration that is going up like this. Let's let it be 5 meters per second squared. And let's define this angle. That angle looks to be 40 degrees. We'll go with it. Okay. So now I'm going to define my piece that is parallel to the x-axis up here, and my piece that is parallel to the y-axis, it didn't change color, over here. And now if I write, switch back to green because I can, the sine of my 40-degree angle is the opposite side, but that's the side that is parallel to the x-axis, which is going to be ax. I guess I should have labeled these, so we'll define them now. Ax divided by a. So that's ax divided by 5 meters per second squared, or in other words, ax equals 5 meters per second squared times the sine of 40 degrees. And if I put that into my calculator, 5 times the sine of 40 is 3.2 meters per second squared. And if I look at my y component in purple here, cosine of 40 degrees is the y component divided by a. So that would be ay divided by 5 meters per second squared, or in other words, ay is 5 meters per second squared cosine of 40 degrees. So 5 times the cosine of, is 3.8 and change meters per second squared. Okay. So 2 examples, one where the x component was found with a sine, one where the y component was found with a sine, and it all depends on how you set up the triangle. The best advice I can give you is to always go back to the definition of the sine, the cosine, and tangent. Draw a triangle, go back to the definition. If you get into the habit of doing that, you won't get into the habit of y component is always sine. Okay. One more thing. Let's pretend for a minute that you knew ax and ay, and you wanted to find the angle. Okay, so I'm rearranging the question here a little bit. So if you knew ax and ay and you wanted to find the angle, then what I would do would be the tangent of the angle is the side opposite. That's AX divided by AY. AX is 3.2 meters per second squared. AY is 3.8 meters per second squared. If I take that ratio, 3.2 divided by 3.8, I get 0.84, and that equals the tangent of theta, which means, oh, I don't know where that came from. Theta is the inverse tangent of 0.84, which gives you 40.1 degrees. So it did return where we started within round off, because these were not exactly 3.2 and 3.8, but it got us close. Okay. In the next unit, we will do some more examples and look at how we add and subtract vectors when we have components.